In 2017, Oumuamua sped up. Now, the new interstellar visitor, 3I Atlas, flips the script. It shows a visible coma and yet appears to be slowing down. How does a comet brake while heading toward the sun? We trace the data shift from acceleration without a tail to deceleration with a CO₂ heavy coma. We test the hypotheses. Is it a reverse solar sail, active propulsion, or simply gravity choreography? Storytime with two travelers. In 2017, Oumuamua puzzled us by speeding up without a visible tail. Now, 3I Atlas flips the script. It shows a visible coma with unusual chemistry and, according to several teams, a tiny but consistent deceleration near the sun. Today, we'll trace that shift from acceleration without outgassing to deceleration with a CO₂ heavy coma, and explain what each behavior says about material, spin, and forces. Then, we'll map the next checkpoints: Perihelion in late October, November-December tracking, and a potential March 2026 Jupiter flyby that could reveal whether we're seeing steering or subtle physics. From Oumuamua's push to Atlas's Slowdown one, sped up with no visible tail. The other wears a bright coma and yet seems to slow down. Here's what changed: the force budget. With Oumuamua, we lacked an obvious push. With 3I Atlas, we see gas and dust, but face a reported loss of speed along its track. That flip forces us to ask whether we're seeing new physics, an unusual geometry of jets, or early data fooling us. Quick definitions so we're aligned. A coma is the fuzzy envelope of gas and dust that forms when sunlight warms an icy nucleus and material escapes. Non-gravitational acceleration means any change in motion not explained by gravity alone. Things like outgassing thrust or pressure from sunlight. An interstellar object is one that comes from beyond the solar system, on a path that isn't bound to the sun. Now, to the tension point. Several teams report that 3I Atlas shed roughly 0.3 kilometers per second of speed over 3 days, from about 68.2 to 67.9 kilometers per second relative to the sun. That's a micro deceleration compared with its total speed, but it is directional. The mainstream expectation is simple. Inbound motion speeds up under gravity. Add outgassing, and you usually get extra acceleration or sideways steering, not a steady braking along the orbit. If the trend is real and aligned with the path, it strains the typical Comet playbook. Outgassing acts like a tiny rocket. Sunlight heats volatile ices, sublimated gas vents, through pores or jets. The escaping flow carries momentum. If a jet points mostly sunward, the reaction can nudge the body outward or twist its rotation. If jets are patchy, they change over hours as the object spins, causing jitter in the trajectory. But a persistent slowdown along track toward the sun requires thrust that systematically opposes motion. That's hard to sustain unless jets are finely aligned and stable, or unless the body has unusual shape and spin that keep the thrust vector pinned against the velocity direction. Oumuamua is the reference case that set the stage. It showed a small acceleration away from the sun, yet no detected gas. Natural hypotheses tried to supply hidden thrust. Hydrogen outgassing would be efficient, but hard to preserve over interstellar times. A nitrogen ice shard could shed mass cleanly, but demands rare parent bodies. A fluffy fractal dust aggregate could have huge surface area for sunlight to push, but the structure must survive heating and rotation. Each hypothesis matched some clues and missed others, which kept the debate open. For 3I Atlas, the data thread is the story. Reports cite spectroscopy from the James Webb Space Telescope, radar-derived velocity solutions from ground facilities, and Doppler tracking using Mars orbiters. When different instruments, wavelengths, and methods agree, confidence rises. Spectra probe the gases and dust temperature. Radar pins down line-of-sight speed. Orbiter Doppler adds an independent check via radio links. If all three trace the same velocity drop, it's less likely to be a single instrument quirk. Still, early measurements carry pitfalls. Astrometry can drift if star catalogues or distortion maps aren't perfectly applied. Non-sidereal tracking, moving the telescope to follow a fast target, can smear or bias signals. Solar radiation pressure, the photon push from sunlight, needs careful modeling because area-to-mass ratio and reflectivity change the effect. A small geometry change over a few nights can turn systematics into an apparent trend. Chemistry adds another layer. A reported CO₂-dominant coma near 95% points to volatile ices venting at relatively low temperatures. CO₂ sublimation can produce strong jets, especially near the sun. But a net along-track slowdown still isn't the straightforward outcome. Jets prefer to steer or nudge outward unless they're arranged to counter motion. You would need an asymmetric vent layout that stays aligned over many rotations, or thermal lag that peaks thrust at just the right phase angle. So the working takeaway is narrow but useful. If the deceleration is real and along track, conventional comet physics struggles to keep the thrust vector locked. If it's an artifact, better calibrated post-perihelion data should flatten the trend. Which raises the next question. What plausible mechanisms, natural or technological, could create a true break in sunlight, and what upcoming checkpoints can separate them? 3 hypotheses on the table and how to falsify them. If an object seems to break in sunlight, is it a sail, a drive, or just gravity playing a clever trick? Let's turn that into 3 testable ideas. We'll treat each as a hypothesis, spell out what would make it work, and define the observations that could knock it down. The goal is not to pick favorites, but to lay out ways the data can decide. Hypothesis 1 is a reverse solar sail. Solar radiation pressure is the tiny push from sunlight. Photons carry momentum and bounce off surfaces. If you had a large, thin sheet angled against the motion, the net pressure could act like drag with respect to a sun-centered path. That needs area-to-mass ratio to be high and the surface to reflect efficiently. It also needs control. The reported rotation looks steady so far, which complicates the orientation needed to keep the sail braking, rather than tumbling out of alignment. Natural bodies rarely hold a fixed attitude in changing sunlight without torques reshaping the spin. An artificial sail could, but then attitude control must show up in other ways. Here's how we would test it. If the surface is acting like a sail, brightness should change with phase angle in a patterned way, not just randomly with rotation. Polarization, how light waves align after reflecting, should favor a thin, reflective sheet more than a rough, solid nucleus. Thermal inertia should be low if the structure is thin. It won't store heat like a dense rock ice body. Near perihelion, sunlight torques peak. If torques act, the rotation state should drift measurably. Even small changes in spin rate or pole direction would support a sail-like geometry under stress from light. Hypothesis 2 is active propulsion. Low thrust drives, like ion propulsion, push gently but continuously by throwing ions out the back. Exotic concepts claim thrust from electromagnetic fields or plasma interactions without exhaust you can see. The obstacle is power. Sustained thrust over interstellar time needs a huge energy source, and that usually leaks heat or radio signals. A green glow near the coma would have to be separated from known chemical emissions to be meaningful. Without that, we risk confusing chemistry with thrust. The test plan is straightforward. Scan for narrowband radio lines that stand out from natural background. Look for a thermal excess that does not fit sunlight heating and re-radiation. Watch the light curve for periodic changes that repeat in sync with any claimed thrusting pattern. Then, compare all signals against known spacecraft thresholds. If a drive is strong enough to change the path by tenths of a kilometer per second in days, the byproducts should sit above well-established detectability limits. If no plume, no heat, and no radio show up, the propulsion hypothesis weakens. Hypothesis 3 is gravity choreography. A gravity assist is a clean energy swap. A flyby steals or adds a bit of speed by bending the path in a moving planet's frame. Mars this October and Jupiter in March 2026 offer chances to reshape the trajectory. The claim here is that precise timing could mimic a slowdown without thrust. The catch is odds. An interstellar arrival randomly threading multiple assists at useful angles is not impossible, but the probability is low without prior steering. We can test this with navigation-grade tracking, compute pre- and post-encounter residuals, the small differences between modelled and measured positions and speeds. If the changes stay inside uncertainty bars after accounting for any outgassing, gravity alone suffices. If they exceed the error budget in a directional way, and that pattern repeats across encounters, steering becomes the stronger interpretation. So here's the practical roadmap. Perihelion in late October gives us torque tests and thermal checks. Velocity tracking through November and December will confirm or erase any along-track slowdown. The Jupiter geometry in March 2026 offers a clean laboratory for gravity-only predictions versus observed deflection. If the sail hypothesis is right, we should see phase and polarization signals tighten. If propulsion is active, radio and thermal clues should rise above noise. If gravity choreography rules, the residuals will sit quietly inside the models. From there, each new data point narrows the field and moves the claim from attention-grabbing to testable.